Okay, we're going to be talking about gravitons and gravitational waves. And they're theoretically analog of photons and electromagnetic waves. Well, the photon is the particle I showed you, and the wave is the wave. So we're going to be looking at gravitons and gravitational waves. Gravitons are nothing more than waves of photons, actually, or magnetic particles, electromagnetic particles, which everything is, and photons are the smallest ones. All right, here it is. It's all big news about these gravity waves. They're trying to figure these out. And there's a guy at Harvard I'm going to contact. Let me just show you. All right, so I think we found the gravity waves. These are, again, the gravity waves they're looking for, and this is all in the news. And they show a black one here and a white one over there, and entangled fields. Well, that's a dipole. Now, we also found these same things. You see this? A black one, a white one, entangled fields. And these are the little Doppler effect concussion waves coming out from the interaction of the dipole spin. It's a little hard to explain, but the faster they spin, the stronger the field is. And this one I think is Venus, because it has two fields. It has a real tight inside field and a far out field here, but runs down the same axis, which is it's spinning backwards and rotating forwards. So it's kind of crazy. And here's the blue on the moon, which is the blue shift of the moon pushing light and not spinning. In order for something to be a dipole, it has to spin. And the reason it gets to be a dipole is because it's interacting with a whole bunch of other polar particles. And it charges up and discharges, basically the same as these light particles. These are nothing more than dipoles, too. And that's what they see in space, and that's what we see, too. Here it is right here. These are all magnetic fields. And you see this? I don't know what this is behind the moon. But we're seeing all of these fields coming out here, and it's a very, very tight separations here until it gets way out here, and then it dissipates. But that's how these spinning things do in space. Now it could even be the sun. I don't know. It seems to be something bright behind it. And this is the moon. And I don't think it could be the sun, but I don't know. And this is the blue of shift, because the moon is moving this way, crushing the light, turning it blue. It's turning a little bit reddish here as it trails forward, just not much. But you can see a little bit of a red drag on there. You see it? But up at the top, it's quite obviously crushing the light, turning it quite blue. And that's expected. That's understood. But that's not why the universe is expanding and pulling the light. The universe is not necessarily expanding. The universe, the light is coming real fast when it starts out from far away, and as it comes, it gets slower and 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 slower as it comes through all these fields and particles in space. Space is not empty. They know it's not empty, and even Fermilab says space is not empty. It's like a bubbling foam. As the particles coming through space hit these particles that are just floating around in space, they clink on and off like a dizzying display of on and off subatomic particles. Exactly what the words say from Fermilab. So light slows down. There's no question. We show it slows down, it speeds up. It's two particles. You get a Whistler wave. You get the concussion wave here. The explosion is here. Dark matter, white matter, call it what you want. There are two different types of bosons. And this is the only thing that's in question right now for me, is what style of a nucleus is it? Is it a layered nucleus or is it a congealed nucleus? And then this is what changes from the standard model. And the gluons are nothing but actually electrons. That'll invade something and warm it up. That's why warm things weigh more. They'll just work their way in as warmth. This is different. These bounce off you. Light bounces, that's why it's got a field all the way around it. So they're like stable particles. These are unstable. They want to attach to something, incorporate into something, burn into something. It depends on how much pressure is behind them. And the same thing with the photons. It's I've shown a whole bunch of experiments, and I'll show a bunch more, using actually the Crookes radiometer right here, and then using ultraviolet and infrared and heat and cold, and the different lasers, the red and green and blue lasers, and see, point them at the different veins, the white side and then the black side, see if it does anything. Point the light straight down on it, what happens there. I think it's the glass that is causing this, but nobody knows why these things work. And nobody has any idea. There's all kinds of theories. Oh, it's thermal transpiration. Well, there is something to do with that. I don't disagree with that whatsoever, but I have a whole new interpretation, because the difference is in the thermal transpiration between outside the glass and inside the glass. And it loses energy once it passes through that glass. That's why you don't get sunburned on the other side of a glass of a window. If you're outside here, you get sunburn. If you're inside the other side, you don't get sunburn. The glass is what's taking away some of the energy. So we're going to go through that too. Okay, they're looking for the gravitational waves, but I don't think they found them. And they say they're caused by gravitons. So the gravitons are to gravitational waves, the theoretical same thing as photons for electromagnetic waves. And that's right there. That's like a photon, and this is the wave around it. And as it moves through the air, it creates a wave. All the other particles have to get out of the way. So that's the key. And as it goes through, it flips and it flips and it flips as it charges up and discharges. And that's exactly the same as the gravitational waves, because they are formed from the same things as light waves, which is the photons. It's just that they're much more energetic because they're formed from an interaction of the spinning planets or sun or whatever it is. They create these huge waves of magnetism. Well, let me show you on the sun. I can show you this coming off the sun very easily. Now check this out. Take your time and think. This is a solar eclipse. It means that the moon has completely covered the sun, and the moon does not emit light, so it blocks the main blast of light that would hit you in the face, and you couldn't see any of this stuff. You don't see that normally. Solar eclipse is very unique. Now, what do we see? And you have to take your time and look at this and think, and just say, "Ooh, that's nice," and let's think about it. You see all these little tiny rays? One right after the other, 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 over. Same thing at the bottom. All right, you see that? Those, my friends, will wrap around way out and come back to here. These are the same waves that I have been showing you here. Right here. And way down here, there's a bazillion of them coming out of the ends of whatever this is. And I think this is Venus, because it has like two fields in here. They should only have one. But Venus is an unusual character. It spins it spins backwards. It's supposed to have the right hand spin. It spins left hand. However, it follows the rest of the planets in a circular orbit in the normal way, which would give it a different field, possibly. I don't know, I'm just guessing. But this is not normal to see two fields, one overlapping the other, coming straight out of the same poles. That's not an accident. This is something that's a standard for this. And also you see this very intense dipole. And also this is spinning backwards, which will give it an extreme intensity. It's not just a nice black and white. It's really black and white. All right. Normally you're going to see them like this. You know, sort of black and white, not getting crazy like that other one. That thing is just off the scale wild. Now, so let's get back to the sun. Again, we only have one set of lines coming out, so it has a normal field, but it's going to go way, I mean, millions of miles out and comes back around here. They're huge fields. As I showed you, they're huge fields. That's why I'm going to keep jumping back and forth, because it's hard to even think about the possibilities here. Hold on, where is it? Look at how big these fields are. Look at the size of them. Look at the size of these fields. These are not little puppy fields. These are not little tiny things. And there's some strange stuff going on out there. But all of these have a black and a white to them. They're all dipoles. And whenever you see a dipole, it makes a field as it spins. That's just what it is. And there's some things I really can't account for. I have to be perfectly honest with you. But I'm getting pretty close to figuring out most of the things. It makes sense to me. Let me just go with that. Now, and I'll also, let's get back to the sun. There's our plane of spin. So it's spinning this way. It's spinning, and I know for a fact it's spinning this way. And it is because of these. You see these three spots? That's the red glow of rub. That's the rub of the planet of the sun scrubbing this way as it spins and plowing that way going forward. And this is the side that sloughs off. You see these huge magnetic fields around here? These are just gigantic magnetic fields, and they're going out the sides. Don't forget, these are the ones that are going to go way around and come back to each other, as I showed you in the other actual fields. Now, these are just bright lights of sunlight, which is confined into these interference patterns. Basically, you would call these interference patterns. Exact same thing. The whites don't want to be next to each other. They push each other apart. This is not unknown. They just don't associate it with all of the other things like I'm showing you. Coming through the Venturi, they come out like this. They don't want to be next to each other. They hate each other. Let me show you coming through a Venturi how separated they are. It's identical. Well, let me show you. All right, this is light interfering with other particles of light. And when they do, they glow like crazy. So they want to try to stay in a perfect arrangement of staying away from each other. And that is exactly what happened coming through the Venturi. Look at this. This is spectacular. Look at this. This is light through a single Venturi, and it's spinning this way. And this is the impression on the wall in the back. Now, as the light comes through, it's actually like a drill bit. You can see it. But you see how finely these lines are? Those are just exactly like the ones coming out of the sun. Because we're cramming all of those particles through here, and when they get on the other side, they don't want to be together. They just go choom, and they could set up these absolutely flawless lines coming out here, and they call them interference patterns. Now, when they use a double slit, they get all gobbled up together. But these are exactly the same as these interference patterns here. Identical. Identical. Now, don't forget, this is the extreme interaction area. Extreme. That's why it's red and it's glowing, and all of these big fields are here, and it's shooting out solar radiation just everywhere. Everywhere. Now, this is the trailing edge, but it's still hotter than hell. I mean, it's shooting out, it's scrubbing through and being ripped through. You see it here? You see it coming out here? This is like, whew. This one's hitting head on and scrubbing into it, so we don't have that. We have a push out this way. This one has a trail off. That's the difference. You have to really look at things very carefully, otherwise you miss everything. I missed everything for my whole life. Now I don't miss much. But I take my time. And you don't see any of that redness here because it's sloughing off. Here it's got to plow into it and spin into it and push into it at the same time. That's why I know it's spinning this way, pushing that way, and creating these extraordinary amounts of magnetic radiation. which makes this into a just gigantic dipole. This really says it all in one picture. The dipole, extreme dipole here in this particular case, having extreme concussions down here and then slowing down as like a Doppler effect goes, and by the time it's out here, it's lost its really magnetic influence. Here's the moon, and here's the red shift or orange shift as it moves this way, and because it's being pulled away from light for some reason. It's turning. Well, I know what it's. This is not really red shifted. This is hard for you to understand, but this I know is moving this way and concussing, making this shift to the blue. That I understand. Light is hitting it from this direction out here. And as it pushes into that light, it will turn it blue, yes. So it's like dragging out of the light. The light is trailing off here. Let's put it that way. It's not really shifting red like the light is it's pulling away from a light source. It's not that. It's just sort of drifting through. So it appears a little bit red shifted, but that's not the case. All right, this is my claim, and this is what's observed. The Earth is, let's say, let's just go with 100 degrees around the whole Earth. And then out here, way out here at the ionosphere, where it's extremely hot, and all there is ions, which would mean all there is electrons, it's 2,700 degrees, 3,000 degrees, something like that, way out here. Why would it be that hot out there? And then right below that, it's minus 80 degrees Celsius. I think that's like, I don't know, 150 degrees below zero or something like that. Way, way, way cold. How come it's hot, then cold, and then hot again? The colder it gets between these two layers, the hotter it will get on Earth. Because the hotter it is out here, the colder it gets below. The colder it gets below, the hotter it gets below. It's a dipole nature of these things. That's why we're heating up, even though this middle layer is getting colder. They say, well, it's getting colder, so it doesn't have anything to do with us down here, global warming. No, it's all expansion of everything. And the hotter it gets way out here, because the more scrub it has, the hotter it's going to get way down at the bottom. It's going to get colder in the middle. It's just the nature of it. The sun is the same thing, 10,000 degrees on the surface, 10,000. Millions way out here where we saw the enormous amount of radiation that has to get past all of the particles it's scrubbing through. We have an atmosphere that ends out somewhere about there, and it looks like this. All right, this is above our atmosphere. It's just above it. This is where the ionosphere is. You see this? 1,500 degrees Celsius. It's like 2,700, somewhere around there, even more. It's just nothing but ions. It's the ionosphere. Ions are electrons. Now, right below it is the coldest layer. It's minus 80 degrees Celsius. There's a tremendous difference in temperature. And this layer designates the difference because this is dipole. And then below that, it gets warm again. So it's hot, cold, hot. And then there's other layers of here that protect us from certain high energy particles, which are like the ultraviolet rays and so forth. Because by this time, we're starting to get a little bit of a dense atmosphere. And it's dense enough to counteract most of those impacts of those heavy-duty particles, cosmic rays, ultraviolet, X-rays, all that stuff. But it still gets hotter down here, so it's cold, hotter than hell up here, and everything burns up coming through here. You know, it depends on how it comes through, and it depends on what the material is. So don't say we can't get through here. We can easily get through there. It's just that you have to do it in the right way, and sometimes meteorites will come in sitting in that layer for a pretty long time, and they'll just completely roast up and explode and do all kinds of things. Sometimes they come straight through and they're not too damaged. And I have several meteorites here, and some of them are in pretty good shape. So anyway, that is what happens. The reason for this scrub is the reason for global warming. I'm showing all these fields, they're everywhere. So light doesn't travel at the same speed. We know light can slow down and speed up. I've shown that so many times. It's just regurgitation now. That's speeding up. And nobody can deny this, so don't try to, oh, it just looks like that. No. And this is slowing down. No, it doesn't just look like that. It is slowing down. And light goes faster and slower. The green and the red are totally different and have much different values when they concuss. And it just goes on and on and on. I don't know how I can get much deeper into it than this. But I think what I'm going to do is play Sabine's whole video because she does such a nice job. And she's conveying what science news is. This is science news. So I'm using this under the Fair Use Act. I'm not stealing anything from anybody. I have commented on what I say these particles are and what they do and what they look like. And these are actual physical pictures of them. These aren't just doodles, drawings. These are the real things. This is a doodle, but that's not mine. That came from CERN or somewhere. And that's a doodle. That came from CERN. And that's from Atlas, I think. Another doodle. But anyway, let's see what Sabine has to say. Oh, by the way, this was the fellow that's doing this at the Department of Physics at Harvard. So I'm going to contact him. I'm going to send him some samples of the stuff and see if he's got any interest. But she mentioned him, Qumran Vafa. Now, it says he's been studying this stuff for 4 decades. This is Qumran Valda. Primary area of research is in string theory, which is in these depths of the atomic structure. String theory, a subject that is about 4 decades old. That's not true. Electron flood theory, dipole flood theory, I had in 1970. So that's 50 years old. So I win. Is at the center of efforts by theoretical physics to find a unified fundamental theory of nature. I have found it. It's dipole electron flood theory. String theory produces a framework to unify everything we know about nature, which is what I have done, including all particles and the forces between them in a consistent quantum theory, precisely what I have done. This is an ambitious goal, given that it aims to describe physical phenomena involving scales that are 10 to the 25th times smaller than the atom. Well, I don't necessarily go along with that, but let's just keep going. As well as the cosmology of our entire universe. And yes, that's for sure. We have to take into account. Is it expanding? Is it contracting? What is it doing? It involves a scale of about 10 to the 37 times bigger than the atom. All right, in a single theory, we have to make this happen, and I have. So it's got to be in a single theory. One studies the mysteries of confinement of quarks inside atomic nuclei, as well as enigmatic properties of astrophysical objects such as black holes. Exactly what I'm doing. Exactly identical what I'm doing. So I'm hoping he will respond. I'm sending him an email with all of my information. Who knows? We'll find out. So let's go to Sabine. All right, I'm just going to take it from here. It's only 8 minutes long, the whole thing, but we're in about 2 minutes and 45 seconds in. And you can come up and watch the whole thing. She's very engaging. Okay, here goes. This is the guy that I'm going to get a hold of right here. And here's what it says. Here's what she says.
This old idea of large extra dimensions. Indeed, these dark dimensions are a new research program that seems to have begun in 2022 around Qumran Vafa, a string theorist at Harvard who has been doing this stuff for decades. In their scenario, there's one extra dimension that is particularly large, and they ignore the other 5 as being too small to be measurable. This is not new. It was a rather
let me just say something. I agree with that. They are too small to be measurable, that I can tell, because they are surrounding the nucleus, and they're packed in a certain way where they achieve stability at certain quantities, where they fill in each little void. There's something to do with that, and they get bigger and bigger, and there has to be something to do with a vibrational, they talk about all these things being created at the dawn of the universe. I don't believe that that's the case. I think they can be ripped apart and put back together quite easily, actually.
common setup 20 years ago. The new thing is the justification for why this one dimension has a size of about 1 micrometer. This is supposedly natural because it's related to the cosmological constant and something with the swampland.
Let me just tell you something. Anything when you hear somebody say it's a constant, it's a law, it's an invariable, it's nonsense. All of those things are crazy, like the speed of light. It's so obvious now that we've been going down the wrong road because of being forced to do the laws and all the constants and all these things that they come up with. It's because they come up with them. Only the way they come up with them is because the only way something will work is if they come up with something nonsense to make it work. And that's what's happened. I go by the nature of things, the reality. So she's talking about a swampland, but she's right about that.
Doesn't really matter exactly what this means because the swampland isn't real and naturalness arguments have failed over and over again in the past. In any case, this supposedly natural size of the extra dimension is great because, guess what? It could be tested with one of the next experiments. The current experimental constraints on the size of this dimension is currently about 52 micrometers.
All right, let me just say, if she's talking about the radius of the field surrounding an electron, I don't know exactly what she's talking about, whether it's surrounding a dark matter particle or an electron or an atom or not. She's talking about 52 micrometers, the radius. So that would be 104 for the diameter of the whole thing. But 52 is 0.002 inches. That's a pretty good little distance. It's not a big distance, but I think it's actually much bigger than they're talking about. Although all my magnets here have literally hundreds of thousands of particles in them. So that they're not just one. I don't know if it's a direct relationship if you divide it by 100,000. But anyway, there's a good size effect coming out of these particles, the magnetic effect.
Okay, but what does this have to do with dark matter? Well, in such large extra dimensions, you must assume that forces which we have measured on very short distances, that's the nuclear forces and also electromagnetism, don't notice the additional dimensions. And actually all the matter that we are made of can't travel into these directions either. In string theory speech, the normal matter is confined to the brain. That's B-R-A-N-E, not B-R-I-A-N, is derived from membrane and is our normal three-dimensional space. So all the normal stuff needs to stay on that three-dimensional brain. The reason is that atomic nuclei are much smaller than this micrometer, which is the supposed size of the extra dimension. And if the constituents of nuclei could spread into more than 3 dimensions, nuclear physics wouldn't properly work. But here's
all that stuff is kind of nonsensical, to be perfectly honest with you. That particle that she shows sending inside the brain, here, hold on. That particle is the photon. All right, and if it's an atom, it's the core of the atom. But for me, it's the photon, and it has a surrounding field, yes. So you can call it a membrane, and the field surrounds it. Yes, I agree with that.
Than 3 dimensions, nuclear physics wouldn't properly work. But here's the thing. There's no such problem for gravity, so they can assume that gravity does experience the large extra dimensions. And these extra dimensions then explain dark matter as follows. Whenever you've rolled something up, you get standing waves in this rolled up direction.
All right, let me just tell you something. She's right about the standing waves. I've shown them those waves, and those are what they call a gravity wave. So here goes.
For gravity, these standing waves are quanta of the gravitational field called gravitons. And if they are standing waves, they have masses that depend on how many wavelengths fit into the extra dimension.
All right, let me just jump over here because I want to be sure you understand that. She's talking about these gravitons, which are the field waves. And here they are right here in our experiments. All right, these are those field waves, very, very close to the source emitter. You can't even tell they're here, but they're, I mean, just so. That's why it's so intense. Anytime you push and shove some of these particles together, you get a glow, and it starts to get a little less, and it gets less and less and less. But you still got the black pushing. So that just I show you. That's the concussion waves. And hold on a second. All right, don't forget, she's talking about these massive gravitons, which are the gravitons that create the gravitational waves. And here it is right here. You call them whatever you want. They're pushing out. They're magnetic waves. And they get really intense when they're close, when they first emitted, and then they just diminish out, just like the Doppler effect does when they slow down as they get further and further away. And light does the same thing. Light slows down. All right, let me go back to Sabine. Hold on. All right, so she's back into the standing waves. Take two.
Quanta of the gravitational field called gravitons. And if they are standing waves, they have masses that depend on how many wavelengths fit into the extra dimension. These massive gravitons can make up dark matter. Again, this isn't a new idea. This is the...
she's right. It does. They do. And I showed that. You can see them. So she's right. Or somebody was right. I don't know. But I can show that that's true. You see, that's the black particles. There's black in each one of these, I think. But there's certainly the one in the front, and it's being vibrated forward, which creates that Whistler wave. Look it up. It's a audible wave, and then you get your heavy-duty wave here. So she's right. You can push. All right, so let's go back to it again and make sure we get this right. All right, we got Sabine, take 3. Here we go.
Road up direction. For gravity, these standing waves are quanta of the gravitational field called gravitons. And
when she says quanta, it just means that one is this one, one's this one, one's this one, one's this one, one's this one. Those are all different quanta distances. All right, so let's come back again. Take 4. Oh, Sabine, you are on fire. Here we go.
Waves in this road up direction. For gravity, these standing waves are quanta of the gravitational field called gravitons. And if they are standing waves, they have masses that depend on how many wavelengths fit into the extra dimension. These massive gravitons can make up dark matter. Again, this isn't a new idea. This is the same thing people did 25 years ago. They were even looking for this stuff at the LHC and didn't find it. For this new theory, they just use some parameter ranges that have not yet been excluded. The novelty of the dark dimension scenario is now that the extra dimension doesn't have the same radius everywhere. This has the effect that the mass of these gravitons isn't the same everywhere, and the heavier ones can decay into lighter ones. This basically heats up the gravitons with lower masses, and since they're hotter, that changes the behavior of the dark stuff. They say that this heating effect would affect the large-scale structure of galactic filaments, and guess what? That future experiments could soon rule that out.
All right. She's going to go out on a limb here. She says, now, this filaments and all that business, particles will clump together. And there's a lot to think about here, but you got to start with understanding the nature of the particles, and that's the key, right? It's a moment.
You know what? I'll go out on a limb and say they won't find any evidence for the decay of these massive gravitons.
Well, I'm not sure about that, Sabine. Let's think about it. Here goes.
Yeah, I coincidentally noticed that if you ask Google for my cell phone...
Oh, she's talking about her cell phone now. Okay, I don't know where I am in this presentation at the moment. A lot of interruptions, but we're just going to go into the dark matter and be sure you understand. I say these black particles are the dark matter, the black ones. They have found them years ago, and they are attached to a white particle which has all the glow and no weight. This is fully confirmed by Fermilab, which is these are the particles, and this is actually from the Fermilab point particle article. And this says it's black, its fixed size never changes, has a glowy edge, and that's exactly what we found here. And we were able to separate these particles using a Venturi, and we did that right here, which is what they also say they want to do, is create sterile muons, which is the black one all by itself, and the white ones go through and make a shower, and which is what we did. We accelerated light, we can slow light down, so that's off the table. There's a lot of things that really have to change. They're just not right. And we're going to be talking about dark matter, dark matter, and Sabine Hossenfelder is going to be talking about it in a second here. And she's talking about extra dimensions in the dark matter. And when they say extra dimensions, here's what's... It's hard for you to understand this without being really into physics deep, but every proton consists, in my world, is the dipole electron flood theory. There's 1,823 dipoles, which means a positive and negative together. However, the black part can go to the center and be crusted by the white part, and it always is. Now, is it in layers, though, or is it just all the black go to the center? Here's the other model I have of this. So don't forget, these are glowy particles right next to each other, just pushing each other apart, holding tight. Now, there also could be the blacks between each layer, and that would look like this. It would look like this. All right, you still have a black core, but every time you had the white, you'd have another black, and then you'd have the white, and you'd have another black. And then you're always going to have the white on the outside. That's why we've never seen inside to see the dark matter. The only reason you can see the dark matter in our experiments because it's laying on top of the white. You see it here? It's on top of the white. That's the only reason you can see it. Otherwise, you don't see it here, but it's all over the place in here. It's everywhere. But the only place you can see it is right in where it tries to nibble into the white. You see it? It's all up in here, too. You can just barely see it up in here. You see it? But when it's on top of the white, then you can see it. And you can see very clearly that it has separated from the white. We have the electron showers, because this slit is just as tiny as it can be. It's smaller than that. And they can't get through. So they keep pushing the fields of the white and pushing it out through the other side. And they do push the white because in a different configuration where the Venturi was just tuned just enough to let a little tiny taste of black through, we could see the field, and I'll show you that right now. Here it is right here. This just had just enough to let a taste of black through, see it? The black could get through just a little bit, and here it is, pushing the white. So the black can push the white, and the white has no mass. In the atomic bomb blast, the house burns up. The white hits it, it just burns like this, smokes up. Everything burns. And then all of a sudden the black hits and takes the house down. The black is the pusher. The white is the smoker. And that's got all the energy. It's got 100% of the energy and 0% of the weight. And that's what they say. It's an abstract particle. It doesn't even exist, basically, is what they say, except there's a field there. And I can't disagree with that. And the dark matter makes up almost all the universe, and they can't find it. And it is gravity. And the reason it's gravity is that the white or the glowy parts want to attract to it. It's not that the white or the black wants to jump up and attach to the white. It's that the white wants to come down and attach to the black. The blacks all congregate together, it looks like to me, in more mass than the white. So the white wants to get in there because the black is extremely attractive. That's why lightning goes right to ground, static right to ground, electricity right to ground. The ground will absorb all these electrons. And if it was neutral, it wouldn't. It was just, they wouldn't go anywhere. The ground is the key to everything. And you can have a floating ground. You don't have to have a earth ground. You can have a floating ground. You just have to understand the way this stuff works. It's not all that complicated. If you can get that white apart from the black, it was exactly what we did. Right there. We got the black and the white came through here together and come through the Venturi, all you got is the white. And before it reattaches to the black, which it will instantaneously because the black is just floating around. It seems like it's everywhere. And it just comes right back to it, almost, I mean, it's bazillionth of a second, because this is light. It's going pretty fast. And here it is already attaching back to it. And this is all done with CMOS. And this is the same type of stuff they're using at CERN. Only we're doing it in a more, I think, intelligent way. We're putting it through the Venturi. So we can actually watch as it comes through and watch the particles and see, in this case, they're tumbling. And this is a red and green at the same time. And you can see how weak the red is compared to the green. We did a lot of experiments. And here's the blue coming in real fast and slowing down. And it is two particles, which is a photon like all the rest of them. It spins in a circle. Everything does. Light is a spinner. It's not a flapper. And it accelerates. And it is a wave because there's a tiny little particle in there with a big field. And when you accelerate it, it pulls itself right out of its own wave. Zip, to a Venturi. That's the nature of a Venturi. It's exactly what it does. It's a passive device. You don't have to add any energy whatsoever. And you end up with this enormous, enormous illumination. Illumination is energy. We went from almost no energy to bazillions of energy. Now, as far as I'm concerned, I don't see any reason we shouldn't be able to make free energy out of this. Because it's increasing its energy. It's only going to take a little bit of this to make this thing run. And all the rest, all that white stuff, should be extra free energy. It should be total electricity. Every time you have the white, it wants to get to the ground. So if you run it through the circuit to the ground, you're going to drive your motors or whatever. That's how a car works. It has a bunch of extra white stuff. It doesn't weigh anything. Accumulated in the batteries, has no weight whatsoever. And then it goes out and it gets into the other side of the circuit, into ground. By first going through all the motors and whatever it has to go through, it lights them up, turns them, does whatever, and then it gets back to ground. And when all of those free extra white ones leave and go through and drive all those things, it's just over. Now, they don't weigh anything, so I don't know what exactly does happen, to be perfectly honest with you, but wherever they get to, the ground, I don't know if they dissipate back into the, I don't know. Because you have to fill your batteries back up again with them, and then they go back to ground again. Where they go from the ground, I got to be honest with you, I don't know. All right, all I can tell you is this is basically something similar to what you'd have to do. This right here is where the laser comes through. It separates, you got a ton of white, and then you just put a harvester right there. All right, right up down, before it collects back into the black. So it would be right here. You'd put this electron collector right here. And it would just force those electrons through what's called a photodiode, which means it can go one direction down, and there's a gate in here. Once it gets past the gate, it can't go back. And then it would flood into your batteries, which will have a bunch of little spots that'll take on these little extra electrons, but they don't weigh anything. They don't weigh anything at all. Now, then you have to let them flow through your devices and whatever, and then they go back to this floating ground. And I'm sure, you know, I forget, a long time ago I used to work with all this stuff, but this floating ground is just like a floating ground in a car. So it's nothing special. And this feeds your laser. And that's it. That's as simple as that. And if you could have like this thing here, hold on a second. Hold on, I get my little toy. All right, this is just a Geiger counter. I just drew this stuff to just show you how simple this could be. These are microscopic. That is literal, whoops, that's literally microscopic. And the electricity coming out of there is just unbelievably amazing. You know how you take these little tiny wires, that feed your batteries and everything else, these little bitty wires, and they're running a ton of electricity. This is electricity on steroids. As far as I'm concerned, I don't know. Like, again, this is as close as I can get to doing it, is to show you. Now, once you got all that collection in there, you can do anything you want with it, and it'll be a handheld device you carry it around. And the same thing with a car. And you could plug these into the grid too if you had big enough ones, huge lasers, and you might be able to harvest enough laser light or sunlight to turn it into lasers to do this. I don't know, right now they're just collecting ionization, basically, where the light from the sun hits the solar panel and drives out electrons here and there. Certainly not like this. Certainly not like this. And you could have these in just a whole array of them, and just have all these lasers hitting them at the same time, and on the other side just pump out tons of juice, I would think. And once it gets there, the only purpose it has once it gets here is to find some black. And that's how you do it. You run it through all your little devices. All right, until it gets through and it finds the ground. And then you fill it back up. And again, it weighs nothing. That has no weight whatsoever.